Hello everyone, this is Yuxia from Tohoku University. It's my great pleasure to be here to give the presentation at the CI's 40th International Symposium emphasizing energy transition. Today I would like to share with you our recent work related to the ammonia combustion. The title is Emission Characteristics of a confined non-premixed ammonia oxygen nitrogen turbulent jet flames and oxygen-enriched condition. In the beginning of this presentation, let me simply explain the engine now. First, I would like to talk about the research background. Second, I would like to share the experimental methodology for this work. Third, I would like to talk about the product gas emission characteristics of ammonia turbulent jet diffusive flame and oxygen-enriched conditions. Based on the experimental data, I would like to further talk about the understanding of local flame structure and the characteristics of a confined non-premixed ammonia turbulent jet flames using condo flow diffused flame. Finally, I would like to summarize the main findings from this work. Therefore, let's start with the first part, background. As we all know, ammonia has generated significant attention in combustion community as a potential hydrogen energy carrier and a carbon-free fuel. One way to directly use ammonia is to introduce it to industrial furnaces for the realization of the carbon-neutral society, because around 37% of the world's total delivered energy is consumed in this sector. Generally, turbulent jet diffusive flame is used in industrial furnaces for the melting of the raw materials. There are some issues if you want to directly use ammonia and air condition as a jet diffusive flame. The flame is very hard to be stabilized. Further, ammonia combustion features a low flame temperature and a low radiation heat transfer than hydrocarbon fuels. However, industrial furnaces require particular high temperature. Therefore, the utilization of oxygen-enriched combustion is regarded as an effective approach to enhance ammonia combustion without changing the domestic chemistry. Besides, even though oxygen-enriched combustion can achieve high temperature and high flame stabilizing performance, it may also increase the production of NOx. Therefore, the objective of this study is to clarify the product gas emission characteristics of ammonia, oxygen, nitrogen, non-premixed turbulent jet flames, and oxygen-enriched condition. Therefore, based on the understanding of the objective, I would like to talk about the experimental methodology. Top left side figure demonstrates the experimental setup used for current work. The burner consists of a fuel nozzle and an oxidizer coax nozzle. Mass flow meter were used to monitor the flow rates of the fuel and oxidizer. In the oxidizer, pure oxygen and pure nitrogen were well premixed before injected to the oxidizer nozzle. The oxygen mole fraction was defined by using this equation. Additionally, in actual industrial furnaces, combusted gas such as nitrogen and water vapor circulated and affected the flame and emission characteristics. Therefore, nitrogen core flow was used to simulate this kind of scenario, and the nitrogen core flow velocity was constant at 0.4 meter per second. A non-premixed turbulent jet diffusive flame was developed in a liner to prevent the external disturbance. Currently, we use the Emission wall as a liner. A Fourier transform infrared gas analyzer combined with oxygen and nitrogen analyzer was used to analyze the product gas from the flame. The exhaust gas temperature was measured at the top center of the liner. 3 heat output conditions, including 5 kW, 7.5 kW, and 10 kW flames, were used in current work. All flames are turbulent jet diffusive flames. Based on the ammonia jet Reynolds number, the global equivalence ratio was changed from 0.8 to 1.5 for the clarification of the emission characteristics. The oxygen concentration was varied from 0.6 to 1.0 for the investigation of oxygen concentration effects. Next, based on the understanding of the experimental setup, I would like to share the emission data obtained in ammonia turbulent jet diffusive flame and oxygen-enriched conditions. First, let me introduce the effect of oxygen concentration on the emission characteristics. As we can see from the left figure, it demonstrates the effect of oxygen concentration on the emission and the exhaust gas temperature for 7.5 kilowatt flames. As we can see from top side figure, demonstrated as figure E, it shows the emission of NO and ammonia, and also exhaust gas temperature. The solid line indicates the emission of NO, the dotted line indicates the emission of ammonia. The black line indicates the emission and the oxygen concentration of 1.0. Red line indicates the emission and the oxygen concentration of 0.6. For all oxygen concentration conditions, the trade-off relationship between NO and ammonia was found. It means the emission from the ammonia turbulent jet diffusion flame exhibits the premixed flame characteristics. The optimal equation exists to obtain the minimum NO and ammonia for all oxygen concentration conditions. Further, with the increased oxygen concentration from 0.6 to 1.0, the NO increases and ammonia decreases. Associated to the top side of this figure, demonstrated as the exhaust gas temperature. With increased oxygen concentration, the exhaust gas temperature increases. At this kind of high temperature, it means high concentration of OH and radicals. It can promote the conservation of ammonia molecule to NO. Therefore, NO increase at a high concentration of oxygen conditions. Further, with the increased oxygen concentration from 0.6 to 1.0, the optimal equation shifts to the richer side. Figure B demonstrates the emission of hydrogen. Generally, hydrogen is mainly produced under global fuel-rich conditions, and the global equation is a major parameter for the production of the hydrogen. Figure C demonstrates the emission of N2O. Generally, N2O occurs at global rich conditions, and also it decreases with the increase of oxygen concentration. Next, I would like to talk about the effect of heat output on emission characteristics. As we can see from left side figure, it demonstrates the effect of heat output power on emission and exhaust gas temperature and oxygen concentration 1.0. As we can see from figure E, it demonstrates the emission of NO and ammonia. The black line indicates the emission of NO and the heat output condition of 10 kW. The red line indicates the emission and 5 kW flames. Therefore, for all heat output conditions, the trade-off relationship between NO and ammonia was found. Same with the oxygen concentration effect. Further, from 5 kW to 10 kW flames, the NO increase and the unburned ammonia decrease under the same global equation. Associated to the top side of this figure, exhaust gas temperature increases with the increase of heat output condition. It means more heat can be accumulated at the same time under the high heat output conditions. Further, the optimal equation was shifted to the rich side with the increase of heat output from 5 kW to 10 kW flames. Figure B demonstrates the emission of hydrogen. Generally, hydrogen is mainly produced in the global fuel-rich side, and it increases with the increase of heat output power. Figure C demonstrates the N2 emission and the high heat output condition with black line and 10 kW flames. There are almost no N2 emission. However, under 5 kW flame, there is some N2 emission. Generally, under high temperature condition, the high temperature can promote the N2 decomposition. Therefore, there are almost all no N2 emission under high temperature conditions. Further, we also made some experiments by using uninsulated wall and made some emission comparison between insulated and uninsulated wall. Left side figure demonstrates the comparison. Black line indicates the emission by uninsulated wall. Blue line indicates the emission by insulated wall condition, which I previously explained. As we can see from figure E, by using the insulated wall, there is a 300 Kelvin exhaust gas temperature increases. Further, the optimal equation was shifted to the richer side by using insulation wall. Further, as we can see from figure C, with using insulation wall, there is almost no in-between emissions for all conditions. One important thing is the optimal equation exists for all conditions, and the premixed flame characteristics exist for ammonia turbulent jet diffuse flame. So why this kind of phenomenon happened for the ammonia turbulent jet diffuse flames? So next up, I would like to explain this phenomenon. To understand the local flame structure and characteristics of confined non-premixed ammonia turbulent jet diffuse flame, we do some counterflow diffuse flame calculation by using the chemkin. As proposed by Williams and Peters, the local flame structure of a turbulent jet diffuse flame can be treated as a counterflow diffuse flame structure based on the flame left concept. Therefore, we can obtain the local flame structure of an ammonia turbulent jet diffuse flame by using the counterflow diffuse flame calculation by chemkin. The basic configuration for the calculation is shown here. First, the chemical simulation was conducted by supplying pure ammonia to the fuel side and pure oxygen to the oxidizer side. Left side figure demonstrates the detailed flame structure of the ammonia counterflow diffuse flame. The flame structure of the counterflow diffuse flame is different from the premixed flame structure, as we can see from right side figure, owing to the initial distribution of fuel and oxidizer. In the counterflow diffuse flame, the NO is mainly generated on the oxidizer side, corresponding to the area where all charcoal are generated. And hydrogen is generated from the fuel side owing to the decomposition of ammonia in the fuel side, as we can see from left side figure. Right side figure demonstrates the premixed flame structure and the oxygen concentration 1.0 and the equivalence ratio 1.0. Generally, in the premixed flame, the NO concentration rapidly increase in the reaction zone and gradually decrease away from this zone and corresponding to the area where all charcoal produced. In current non-premixed turbulent jet diffuse flame, it's reasonable to consider that the flame structure near the bottom rim is close to the counterflow laminar diffuse flame. However, with an increase in flame height, the fuel and oxidizer were both diluted by the burning gas and cold flow nitrogen. Based on this, to understand the full ammonia turbulent jet diffuse flame emission characteristics, further chemical simulation were conducted in terms of nitrogen dilution effects on the fuel and oxidizer using counterflow diffuse flame configuration. The fuel or oxidizer ratio was used to obtain emission characteristics under different dilution conditions. An emission index was used also. The emission index was calculated by using this equation. The physical meaning of emission index is the ratio of mass of a species emitted readily from the computation domain to the mass of ammonia entering actually into the domain per unit time. Right side figure demonstrates the emission index and the maximum temperature in the simulation as a function of ammonia ratio and oxygen ratio. As shown in right side figure, at the same oxygen ratio 1.0 with a gradually decreased ammonia ratio from 1.0 to 0.3, the global equilibrium ratio goes to the linear side. Moreover, the hydrogen emission from the full counter diffuse flame increases, and the ammonia and NO emission decreases. In addition, at the same ammonia ratio 1.0 with gradually decrease of oxygen ratio from 1.0 to 0.3, the global equilibrium ratio goes to the richer side. The hydrogen emission and the NO emission gradually decrease, and the ammonia emission increases. To easily capture the difference of emission between full counterflow diffuse flame and the premixed flame, the emission index was plotted as a function of global equivalence ratio, as we can see from left side figure. From left side figure, we can conclude that the emission of hydrogen from full counter diffuse flame continuously decreases with the increase of global equivalence ratio. However, for the premixed flame, the hydrogen emission increases with the increase of equivalence ratio. Therefore, the hydrogen emission has a significant difference between premixed and non-premixed flames. It can be considered that for non-premixed ammonia turbulent jet flame, the turbulent premixing effect is strong. Thus, the emission characteristics are similar to the premixed combustion. Therefore, the rich to lean two-stage combustion concept for premixed flames can be applied for low NOx combustion of ammonia turbulent jet diffuser flames. Finally, I would like to summarize the main findings from present research. Through this work, we clarified the emission characteristics of ammonia turbulent jet diffuser flame under various oxygen concentrations and heat output conditions. We also clarified the wall effect on the emission characteristics of ammonia turbulent jet diffuser flame. We firstly found that the trade-off relationship between NO and unburned ammonia exists in ammonia turbulent jet diffuser flames. Further, the optimal equilibrium exists to obtain the minimum emission of NO and unburned ammonia. We discussed the local corner flow diffuser flame structure and used it for the understanding of the emission characteristics of ammonia turbulent jet diffuser flame. That's all. Thanks for your kind attention. I appreciate any questions.